So now we're going to talk about assumptions. Assumptions that we have when we are doing the simple linear regression. The assumptions are predominantly about the error term. If we write down the model is this, and this is the term about which we have assumptions mainly. The first one is linearity. So it's predominantly about this, but linearity is about the whole model. It just says that there exists a relationship between y and x, and that relation is correctly specified, which means like a straight line is placed through the data and it should represent all the points as best as possible. Like if a relationship is non-linear, straight line cannot fill this requirement. So if the data points are something like this, or even a little bit top, then we can make a straight line through this. So that is why when we do the linear regression, we plot the data first to see if there is linearity in the data. If data looks something, let's say like if it looks like this, if those are the points, those are the data points, and we try to fit a line here like this or like this, then that would not make sense because it will not be able to represent all the points as well as it should. So that's linearity. The second one is normal distribution of the error term. Well, it is kind of self-explanatory what that means, but the implication of this is that since y is a linear function of epsilon, so if this is normally distributed, then y also becomes normally distributed random function. So this is just the implication. Otherwise, normal distribution of error, we know what normal distribution is, so error should be distributed normally, right? Third one is homoscedastic. Now what homoscedastic means is that the residuals have a constant variance, or we can say that the distribution of epsilon I has constant variance across I. So the basically epsilon is normally distributed. So far we have seen it's normally distributed, some mean, and then the variance is sigma square, and this sigma square is constant for across I, basically for all the residuals that we have. And residual is just the error between the observed value and the actual value, the observed and the interpreted value, the value that we found, which is the y I had. So that's the error residual. So what that means, if we want to look at it graphically, is let's say if we plot the dependent variable here and the error over here, then the error should be normally distributed. Sorry, not normally distributed, I mean it should be scattered evenly. Well, you can say it's normally distributed as well though, because if you draw a graph, so this is something that would look like that it's scattered evenly on this graph here. What would not be scattered evenly is if we have a graph like that, and there's a dependent variable, there's the error, and if it looks something like that, right? So that is not evenly distributed. So that's what would look graphically, but that's what it means. Homoscedastic is that the distribution has a constant variance across I. And then the next one is exogenous. What's exogenous? The error term is exogenous. And what that is, the distribution of epsilon I is mean 0 across I. What that means is the expected value epsilon I is 0, right? So for all values of epsilon, the expected value is 0, the mean is 0, which means if we have to write that, it is normal, the mean is 0, and the variance is sigma squared. Now why that is, because let's see, when we have the model as this and we have to write down the regression equation, what happens is, so since beta naught is a constant, the expected value of beta naught is just beta naught itself, right? And this beta 1 is also a constant, so the expected value is beta 1. And when expected value of the error term is 0 and you put these values in this equation, what you get is that expected value of y is beta naught plus beta 1x, and this is the regression equation. Well, that is just kind of like one implication of what would happen if mean of error term is 0. So that's exogenous. Epsilon is exogenous. The fifth one is independence. The value of error, so basically epsilon I is independent of other values. So if the model is that, so when x value changes, the error term also changes with it, but whatever value of epsilon we get, it is independent of the other error term. So if you have to write it down, it just means that value of epsilon for x1 is not equal to, or actually it's not related to, value of epsilon for x2. Well, I don't know what's the symbol for not related to, but that's what's happening. So value of error term for one particular x is not related to the value of error term for another value of x, which means the implication of this is that value of y for x1 is also not related to the value of y for x2. So those are the assumptions that we have for the model: independence, exogenous, homoscedastic, normal distribution of epsilon, and linearity.